We simply don't know, and that answer might surprise you more than you'd expect. What we do know is that 13.8 billion years ago, the universe looked nothing like what we see today. Today, we're surrounded by stars, planets, and galaxies, breathtaking, complex structures stretching across the cosmos. But wind the clock back 13.8 billion years, and none of that existed. No stars, no planets, no galaxies. Just an unimaginably hot, impossibly dense state that we call the Big Bang, the moment most people think of as the birth of everything. But here's where it gets fascinating. The framework scientists use to understand all of this is Einstein's theory of general relativity, published in 1915. And that theory makes a startling suggestion that the universe cannot simply stand still. It must be either expanding or contracting. Space itself should be stretching or shrinking, depending on how much matter fills it. Einstein himself resisted this idea because an eternal, unchanging universe just felt more comfortable. It sidesteps those thorny, haunting questions: what caused the universe? What came before it? Was there even a before? Then came the 1920s. Observations by astronomers like Edwin Hubble revealed something extraordinary. The universe is actually expanding. The very fabric of space is stretching in real time. That discovery pushed brilliant minds like Georges Lemaitre, a Belgian priest, physicist, and mathematician, and one of the true founders of cosmology, to conclude that the universe must have had what he called a day without a yesterday. If everything is spreading apart now, then rewind far enough, and everything was crushed together in a single searing point. That's the Big Bang. That's the picture taught in schools. That's the foundation of modern cosmology. But whether that scorching, ultra-dense moment was truly the very first moment, or whether the universe existed in some completely different form before it, remains one of the deepest unsolved mysteries in all of science. What scientists strongly suspect is that the universe was already in existence before it became hot and dense. There's a powerful theory called inflation, the idea that before the hot Big Bang, the universe was cold, empty, and expanding at a staggering rate. When that expansion ended, all the energy driving it was released into space, heating it up and forging the very particles that make up everything around us, including you. But when did inflation begin? Did it even have a beginning? Honestly, we just don't know. Two great pillars support everything we know about the universe. Pillars built over the last century and still being built today. These two pillars are things you might never encounter in school, but they will absolutely define your university education. The first pillar is called relativity, Einstein's monumental contribution to science. The second is something called quantum mechanics, and it is a truly mind-bending theory. Things can exist in two places at once. You may have heard of Schrödinger's cat. Strange as it sounds, quantum mechanics is our theory of literally everything that happens in the universe, everything except gravity. And today, the place where we push that theory to its absolute limits is the Large Hadron Collider at CERN in Geneva. Right now, at this very moment, cutting-edge discoveries are being chased inside that machine, and within the next year or two, something extraordinary may be revealed. But before we get there, we need to grasp the sheer breathtaking scale of what we're trying to understand. Because the ambition of science, the raw, audacious ambition of it, is what makes it so electrifying. Look up at the night sky. That familiar pattern of stars is the constellation of Orion, visible every winter. Now focus on one tiny, seemingly unremarkable patch of that sky. A patch so small you could cover it with a 5-pence coin held 25 meters away. Almost nothing visible. Completely boring. Or so it seemed. Then the Hubble Space Telescope locked its gaze onto that exact patch and held its camera open for thousands upon thousands of seconds, drinking in every last photon of light. What it captured is jaw-dropping. That tiny, empty-looking sliver of sky is absolutely packed, over 10,000 points of light, and virtually every single one of them is not a star. Every one is an entire galaxy. Over 10,000 galaxies, each containing at least 100,000 million stars like our sun. The most distant object in that image sits an almost incomprehensible 13.2 billion light years away, and it was only discovered in that image just months ago. Light travels at 300,000 kilometers per second. Light travels at 186,000 miles per second, and even at that mind-bending speed, it has taken over 13 billion years for light to travel from the most distant objects in that image all the way to Earth. Now consider this, the Earth itself is only about 5 billion years old. That means most of the light from most of those galaxies began its incredible journey before our planet even existed. And for some of the most distant galaxies, that light was already more than halfway here when our entire solar system was nothing but a swirling cloud of gas and dust, before the sun, the planets, or the moons had even formed. Just picture that for a moment. Remember that tiny 5-pence piece of sky, 25 meters away. Now imagine stretching that across the entire sky. What you get is this, a breathtaking map of the observable universe. Every single dot on that map is an entire galaxy, containing at least 100 billion stars just like our sun. And notice, they aren't randomly scattered. There is stunning structure hidden in there, and we're beginning to understand where it came from. That small line you can barely see, that represents 1 billion light years. Light takes a full billion years to cross it. Now here's a number so staggering it's better to see it than hear it. This is the estimated number of stars in the observable universe, 30,000 million stars. Some larger than our sun, some smaller. Around 350 billion large galaxies and 7,000 billion smaller dwarf galaxies. And that's only the observable portion. There is now strong evidence that the universe extends far beyond what we can see. We're only glimpsing the bubble of space from which light has had time to reach us across cosmic history. The universe is, in a word, enormous. So how could we possibly begin to explain any of this? How do we even know how big it is? How did we figure all of this out from one small planet? How do we build theories about where it all came from, how it began, how fast light travels, what the numbers actually mean? The answer, of course, is science. And one of the most powerful definitions of science ever spoken came from legendary physicist Richard Feynman, a Nobel Prize winner who helped build one of the first quantum theories of electricity and magnetism, known as quantum electrodynamics, back in the 1940s and 50s. It remains our best theory today of how light interacts with matter. So how do we compare our ideas about the origin and evolution of the universe against the cold, hard truth of nature? There's only one way to peer into the vast universe from Earth, beyond our solar system, and that is to capture the light streaming from distant stars and planets. And locked within that light is an almost unimaginable amount of information. This is our sun. And what you're seeing is not a computer graphic, this is real footage, captured by an orbiting spacecraft that watches the sun every single day. It is a dynamic, violent, and breathtaking place. You could fit 1 million planet Earths inside that blazing ball of plasma. 1 million. Every second, it burns through 600 million tons of hydrogen, fusing it into helium. This is a colossus of almost incomprehensible power. Centuries ago, stretching back to Newton and beyond, scientists began studying the light from the sun. After Newton, they discovered a way to analyze it by splitting it into its component colors using a prism, creating an artificial rainbow, just as nature does with raindrops. And here is a modern, high-precision version of that rainbow. Now, rainbows show a beautiful sweep of colors from blue all the way to red. But when you examine sunlight carefully in a laboratory, passing it through a highly precise prism, something extraordinary appears. The rainbow is not smooth. It is slashed with dark lines. Mysterious black lines cutting across the spectrum. Those lines are signatures, fingerprints. the unmistakable marks of chemical elements themselves. Here is why every element is made of a nucleus surrounded by electrons, and each element has a unique arrangement of those electrons. When starlight passes through the gases in a star's atmosphere, hydrogen, helium, oxygen, those elements absorb very specific colors of light, colors that correspond exactly to shifting their electrons between energy levels. Take these two famous lines right here, the sodium lines. Sodium absorbs light in the yellow part of the spectrum. Heat it up and it glows yellow. Why? Because of the precise way its electrons are arranged. So what you are looking at is the chemical fingerprint of the sun itself. By matching those dark lines to experiments done right here on Earth, scientists can read exactly what any star is made of. But here is where things get truly mind-blowing. When astronomers examine the spectra of the most distant stars and galaxies, something deeply strange happens. The dark lines are still there. The same fingerprints, because chemical elements are identical across the entire universe. But in distant galaxies, those lines are shifted, displaced, not sitting where they should be. One explanation could be that the elements themselves are somehow different in remote corners of the cosmos. What's truly remarkable is that all these shifts follow the exact same pattern, and that pattern reveals something extraordinary. So what's actually going on? The answer is breathtaking in its simplicity. The universe is expanding. Every distant galaxy we observe is racing away from us at incredible speed. And that changes everything about the light we receive. Picture light beginning its long journey from a faraway galaxy. Light travels as a wave, and as it crosses the cosmos, the very fabric of space is stretching beneath it. The universe is expanding as that light makes its way toward us. So what happens to the wave? It gets stretched too. The wavelength of the light physically elongates, and wavelength is color. Red light has a longer wavelength than blue light. So light that started out in the blue part of the spectrum, say from a hydrogen emission line, gets stretched across the universe until it shifts toward the red end. The entire chemical fingerprint of those atoms slides from blue to red as space itself expands around the traveling light. That's exactly what we observe. And it's a direct, undeniable measurement proving the universe is expanding. One stunning piece of the cosmic puzzle. Now here's a question that seems almost impossible. How do we actually measure the distance to a star? How could anyone possibly know? It took centuries of extraordinary effort. Going back to the 1700s, the greatest scientific challenge of the era, the equivalent of the Apollo program, was measuring the distance from Earth to the Sun, known as 1 astronomical unit. This was achieved through an ingenious method, observing the transit of Venus when Venus crosses the face of the Sun. By watching from different locations on Earth and applying careful geometry, brilliant minds calculated that fundamental cosmic distance. With that established, scientists used a technique called parallax to reach the nearest stars. What is parallax? Try this. Close one eye, then the other, and watch how nearby objects seem to shift. That's parallax. The slight difference in angle between your two eyes reveals depth and distance. Now scale that up enormously. Knowing the Earth-Sun distance, astronomers observed a star's position in January, then again in July, when Earth has traveled halfway around the Sun. The baseline between those two observations is roughly 180 million miles. The star appears to shift ever so slightly against the background of space. And from that tiny shift, the distance is calculated. Incredible, but true. That's how we measured the distance to the nearest stars. From there, the next step was finding a relationship between a star's brightness and... There are fascinating objects in the universe called variable stars. These stars pulse, cycling between bright and dim in a remarkably predictable rhythm. And here's the stunning part. The rate at which they pulse is directly tied to how luminous they actually are. Scientists call these Cepheid variables. Because if you know a star's true brightness and how bright it appears from Earth, you can calculate its exact distance. The dimmer it looks compared to what it should be, the farther away it is. Then there are Type 1a supernova explosions, some of the most violent, blindingly bright events in the cosmos. We know precisely how bright these explosions actually are, and we can spot them in galaxies billions of light years away. That gives us another powerful tool for measuring cosmic distances. And here's where things get truly mind-blowing. When we look at extremely distant galaxies, their light arrives stretched, shifted toward the red end of the spectrum. This is called redshift. The farther the galaxy, the more stretched its light. And that stretching is a direct, measurable signal of how fast the universe itself is expanding. Because that light has been traveling for 10 billion years across expanding space. If it's stretched by a factor of 3, that tells us the universe has grown 3 times larger during that journey. Using Einstein's equations, we can wind that expansion backward and pinpoint exactly when everything in existence was compressed into a single point. This whole incredible framework is called the distance ladder, a chain of measurement techniques built over centuries, stretching back to daring expeditions on sailing ships that crossed the globe just to measure the transit of Venus. Each rung of that ladder unlocks the next, spanning generations of human curiosity about one burning question: how far away are the stars? Now, physics actually contains several different concepts called multiverses. One of the most compelling is the inflationary multiverse. This comes from our best theory of what happened before the Big Bang. If we define the Big Bang precisely as the moment the universe became extraordinarily hot and dense, something we can actually observe by looking deep into space, then the question becomes, what caused it? The leading answer is inflation. The idea is that before that fiery moment, the universe existed in a cold, empty state, expanding at an almost incomprehensible rate. Then that expansion suddenly slowed and stopped. The enormous energy driving it was released all at once, flooding space with heat and creating every particle that makes up everything we know. That cataclysmic release is what we call the Big Bang. Inflation isn't just speculation, it's a rigorous scientific theory that has made extraordinary predictions, including specific patterns in how galaxies are distributed across the sky. Because that distribution is anything but random. Galaxies don't just drift randomly through space, they flow in vast rivers and streams across the sky, forming a breathtaking structure known as the cosmic web. And here's what's truly mind-blowing. Inflation theory actually predicted this before anyone ever observed it. But the story gets even wilder. There's an extension of that idea called eternal inflation, the notion that the universe never actually stopped inflating. It just slowed down and froze in isolated patches. Picture the very fabric of space-time stretching endlessly, then cooling and crystallizing in tiny pockets. Each one of those pockets triggers its own Big Bang, its own entire universe. Ours is just one of them. What you end up with is a staggering vision, an infinite fractal reality containing an infinite number of Big Bangs. This is called the inflationary multiverse. And it answers one of the deepest questions imaginable. Why does our universe have the exact laws of nature that allow life to exist? The answer might be that every possible combination of physical laws exists somewhere in the multiverse. So it's no surprise that at least one universe, ours, got the recipe right. This is a genuine scientific theory, not just speculation. In its simplest form, it has already made predictions that were later confirmed by observation. There's also the many worlds interpretation of quantum mechanics, a far stranger, almost Marvel movie version of the multiverse idea. Quantum mechanics is fundamentally probabilistic. Think of a quantum coin that doesn't have to land on heads or tails. It can be both at once. Now, how does Earth actually end? The answer is both poetic and terrifying. In roughly 5 billion years, the sun will begin to swell into a red giant. It probably won't swallow the Earth whole. Our planet may drift outward as the sun sheds mass, but it will absolutely scorch it. Earth will be left as a smoldering cinder, likely still orbiting the cooling remains of the sun, a dying ember known as a white dwarf. But here's the brutal twist. We may not even make it that far. Long before the sun turns hostile, conditions on Earth will become too extreme to support complex life. We would need to escape the planet entirely. And there's a far more immediate danger, the very real possibility that we destroy ourselves first. Given that intelligent life may be extraordinarily rare in this galaxy, that would be a catastrophic and deeply unnecessary ending. Out there in the universe, there are certain phenomena, certain extreme cosmic events that make our own sun's death look almost peaceful by comparison. We can measure the brightness of certain cosmic objects with extraordinary precision. Think about how powerful that is. If you know exactly how bright a light source is and you place it far away, then simply observe how bright it appears from where you're standing. You can calculate its exact distance. It's almost too simple. The further away it is, the dimmer it looks. That's the key. Now, one of the most spectacular objects we can measure this way is right here in this stunning image. This is an entire galaxy, an island of 100 billion, perhaps 200 billion stars, each one like our own sun. There are roughly 1 billion stars blazing at the center alone. But look at this. There's something here that appears even brighter than the entire galaxy behind it. You'd think it must be much closer to us, but you'd be completely wrong. This is actually a supernova explosion, a single star sitting on the very edge of that galaxy, the same staggering distance away as every other star in that system. And yet it is shining with the combined brilliance of 1 billion suns. One single star, outshining 1 billion others. This is what's known as a Type 1a supernova, the violent death of a white dwarf star. A white dwarf is what our own sun will eventually become, a burned-out stellar corpse, slowly fading in the darkness. But when a white dwarf has a companion star orbiting nearby, it begins pulling matter from it, growing heavier and heavier until it can no longer hold itself together. Then it collapses and detonates in a catastrophic explosion. We understand this process with breathtaking precision. It was predicted back in the 1930s using quantum mechanics and atomic theory. Because we know exactly what drives the explosion, we can calculate exactly how bright it should be. Because we can photograph it and measure how bright it actually appears, we can calculate exactly how far away it is. This gives us the second crucial piece of the puzzle. We now have two things. We can see that distant galaxies are racing away from us by measuring the shift in their light, and we know precisely how far away they are by hunting for supernova explosions within them. These explosions are rare, on average, just 1 per century per galaxy. But there are billions of galaxies out there. And this remarkable image from the Hubble Space Telescope shows galaxies as they normally appear along the bottom, and along the top, those same galaxies caught in the act, blazing with supernova light. Galaxy, supernova. Galaxy, supernova. Supernovae have now been measured across hundreds of galaxies. From this, a complete map of the universe has been built. We know how far these distant galaxies are. We know how fast they're flying away from us. And what emerges from all of this is something called Hubble's law, and at its core, it is beautifully, almost shockingly simple. The further a galaxy is from us, the faster it's racing away. But what does that actually mean? You might assume we're somehow sitting at the very center of the universe, with everything fleeing from us in all directions. But that's not the case at all. Think about baking bread. Imagine pressing raisins into a lump of dough and sliding it into a hot oven. As the bread rises and expands, every single raisin moves away from every other raisin. If you were riding on one of those raisins, you'd witness something extraordinary. You'd see exactly what astronomers call the Hubble law. The raisins nearby would drift away slowly, while the ones farther out would race away faster, because the entire loaf is stretching uniformly in every direction. All of space itself is expanding at a constant rate. And that produces this breathtaking law, exactly what we observe across the cosmos. The Hubble constant works out to roughly 42 miles per second for every 3 million light years of distance. So step 3 million light years away from Earth, and on average, things are moving away at 42 miles per second. Step 6 million light years out, and that jumps to 84 miles per second. Every 3 million light year step you take adds another 42 miles per second to the recession speed. Now here's where it gets mind-blowing. When you work through the units, the distances cancel out, and the Hubble constant becomes simply 1/seconds, a pure rate. Flip it upside down and you get a time. And that time, that's the age of the universe itself. Run the numbers with our most precise models today, and you land on something staggering, 13.73 billion years, give or take just 120 million. That's the age of everything that exists, measured simply by studying the light streaming toward us from distant galaxies.